Now we're going to look at amino acid catabolism. The bulk of the cell's amino acids are incorporated into proteins, and proteins are continuously being synthesized and degraded. So there is a dynamic pool of amino acids available, but there is no storage form that's analogous to the storage of glucose and fatty acids in the form of glycogen and triacylglycerols. Mammals then can synthesize certain non-essential amino acids and have to obtain the rest from their diet. The essential amino acids must be consumed in our diets. Excess amino acids or dietary amino acids are not excreted, but they are converted to metabolites that are precursors to glucose and fatty acids and are therefore metabolic fuels. General pattern of protein utilization is, number one, the breakdown of proteins to individual amino acids by the action of proteases. Number two, the removal of, get my little pointer up here, the removal of amino groups or nitrogen atoms by transaminases and other enzymes, and we'll take a look at those. There's the conversion of the amino acid carbon skeletons into metabolites such as acetyl-CoA, pyruvate, oxaloacetate, alpha-ketoglutarate, for example. So these are TCA cycle intermediates. And finally, we can utilize these products for energy production or gluconeogenesis. So, removal of those nitrogen atoms. Nitrogen is excreted. It is rather toxic, actually. So, for higher organisms, there's no specific mechanism for nitrogen storage, so that excess nitrogen is removed by some excretory mechanism. In mammals, the major excretory product is urea, as we see here. Birds excrete uric acid, and fish release their ammonia or nitrogen in the form of ammonia or the ammonium ion. The catabolism of the carbon chains vary in complexity from simple one-step reactions to pathways that involve 10 or more steps. In almost every case, the end products are intermediates for glycolysis or the citric acid cycle. So the fate of that nitrogen atom is going to depend upon the organism. There are three key aspects to amino acid catabolism. One, the movement of alpha amino nitrogen atoms from one amino acid to another. And to accomplish this, we need transaminases. So these are the enzymes that are responsible for transferring those amino groups, and they are transferred to either glutamate or aspartate. So glutamate and aspartate are going to be core branch points of nitrogen metabolism, and they can be used to funnel nitrogen into a larger variety of compounds. The second key process in nitrogen metabolism is catalyzed by the enzyme glutamate dehydrogenase. This enzyme converts the alpha amino nitrogen of glutamate into the ammonium ion. This enzyme also functions in tandem with other transaminases to convert the alpha amino nitrogen atoms from any of the 20 amino acids into the ammonium ion. And the final key point or aspect of amino group catabolism is the excretion of that excess nitrogen as urea in mammals. Ammonia, again, is a toxic base which cannot be allowed to accumulate in the human body. We will take a look at the urea cycle next. So before we start dealing with the transaminases, we need to consider the coenzyme pyridoxal phosphate. So here we have the structures of 3 different molecules. We're going to take a look at peroxidine first. This is actually vitamin B6. It's a pyridine derivative which consists of a heterocyclic aromatic ring that contains 5 carbons and 1 nitrogen. There are 4 substituent groups on this ring. We have a methyl group, we have a hydroxyl group, and we have 2 hydroxy methyl groups. The vitamin, which must be obtained in the diet, can be converted into either of 2 coenzyme forms, pyridoxal phosphate, or PLP, which is located here, and pyridoxal amine phosphate, or PMP. And this has an amino group in this position, and we have a carboxyl or aldehyde head group in this position where one of the hydroxymethyl groups was located in the original peroxidine molecule. Okay, so what does this mean? So again, my undergraduate mentor created this slide and a few others that I might have used. Most of the slides are clear and concise, but in this slide, or what this slide attempts to do, is show the transaminase process as it involves the formation of a covalent process between amino acid 1 and the pyridoxal phosphate enzyme. So, what is formed is what we're going to call Schiff base 1, or SB1. Certain rearrangements occur, and the end result is that an alpha keto acid, or alpha Ka1, is formed or released, and we have what we release is, the pyridoxalamine phosphate, and that is now carrying the amino group that was on that incoming amino acid. So we have amino acid 1 reacting with pyridoxal phosphate to form that Schiff base 1. There's a rearrangement to Schiff base 2, and then Schiff base 2 rearranges into the alpha keto acid, and we release PMP. So this is half of the overall transamination process. In the second half of the process, a second alpha keto acid, and we can reverse these steps with this, here we go. The second alpha keto acid floats in and complexes with the pyridoxalamine phosphate to form a Schiff base 2. Thus, the Schiff base rearranges, and eventually an alpha amino acid 2 is released, and the enzyme reverts to its original form. Confusing? Yes, but it works. So let's take a look at the mechanism. And we're going to go through the process one step at a time. The coenzyme is not present as pyridoxal phosphate, but it is actually covalently attached to the enzyme as a Schiff base. So this is the transaminase, basically. What was the aldehyde head group is linked to an amino group of a lysine in the enzyme, and when the amino acid comes in, it reacts with the enzyme and displaces the coenzyme. From the lysine group, the amino acid becomes covalently attached to the coenzyme, and we have the formation of this Schiff base here, in which the amino acid is covalently bonded to the pyridoxal phosphate. So this is the reaction of amino acid 1 with pyridoxal phosphate to produce Schiff base 1. So this is the second part of that transamination mechanism, and this is what is occurring when we convert shift base 1 to the shift base 2 and produce that alpha keto acid and release PMP, or pyridoxylamine. You are not going to be responsible for any of the intermediates here, but you should be able to recognize what the outcome of the second part of this reaction is. So the key point here is that there is a positively charged nitrogen in the bottom of that pyridine ring. And this nitrogen provides a home for an extra electron, And so what we have is a series of electron movements from the quinoid intermediate. One important result is the formation of a carbon-carbon double bond, and we see that here. So we pick up basically an electron, home for that extra electron, and then we see those electrons shifting over here to form a double bond. This double bond flips up. Actually, that's going to be in the second reaction, excuse me. Electrons flip here, and we have the formation of this double bond between these two carbons. When we convert the quinoid intermediate to the ketamine, these electrons are also shifting. Okay, so we're relocating electrons. We lose this double bond. Now we have that single bond. Excuse me. So we're basically rearranging that quinoid so that the double bond between the ring and the adjacent carbon becomes a single bond, and in the process a hydrogen atom is added to the adjacent carbon and we form the ketamine. Finally, a water molecule comes in and hydrolyzes the carbon-nitrogen double bond, and the alpha keto acid is released, and we form that pyridoxal amine molecule. Now, if alpha keto 1 floats off and alpha keto 2 diffuses into the picture, then the process can be run in reverse. So alpha keto 2 is converted to an amino acid 2. This process basically provides a mechanism by which the alpha group from one amino acid is transferred to an alpha keto acid to form a different amino acid. It works. Finally, we want to take a look at that glutamate dehydrogenase before we look at the urea cycle. And this is a multifunctional enzyme which helps to move ammonia nitrogen to and from a variety of organic compounds. And I want you to note here that we have NAD+ or NADP+ involved. And this is one of the few or very few reactions that can use one or the other as an oxidizing agent. Also note that in this reversible reaction, catabolism is running left to right, and anabolism, or the opposite, anabolic process from right to left. So basically, glutamate dehydrogenase catalyzes a redox reaction. So it has a very important role in amino acid catabolism. This enzyme works with other transaminases that can convert the alpha amino nitrogen from the 20 amino acids into ammonium ions. It also has an anabolic function, and that is the reverse. It can convert ammonia nitrogen into alpha amino nitrogen for the biosynthesis of amino acids. So the conversion of glutamate to alpha ketoglutarate is an oxidation, and the reverse is a reduction. And we will take a look at this further after we talk about the urea cycle. So we're going to stop now and go on to urea.